Yeah, awesome. Thank you so much for the introduction. Hi, everyone. Like Yvonne mentioned, my name is Lina. I'm a first-year master's student at the University of Toronto under the supervision of Dr. Greg German. Today, I'll be sharing how we're developing a rapid device to perform phage susceptibility testing for urinary tract infections or UTIs. So antibiotic resistance is rising globally, and for some multi-drug resistant infections, bacteriophage therapy is actually one of the few remaining options. However, phage therapy is not this one-size-fits-all because each infection still has to be matched to the appropriate phage or phage cocktail. Currently, this phage susceptibility testing or PSD process, it's complicated, it's slow, and it's not standardized, often taking hours to days. I've highlighted 4 of the main methods that are currently being used. The 2 solid methods are over on the left, which is the double agar overlay and the spot test. And then the 2 liquid methods that generate a kinetic bacterial kill curve with or without the efficiency of plating are over on the right. These limitations seriously hinder clinical implementation of phage therapy while also delaying treatment options. And a major challenge is that these solid-based PSD methods, they're often not directly comparable to liquid-based PSD methods, which creates that sort of uncertainty in phage selection. Our rapid detection device is designed to not only speed up, but also standardize that susceptibility testing process. It includes a camera-based imaging system, a built-in heater to support bacterial growth, and a reusable cassette where the bacteria and the phage can actually interact with each other. The system monitors growth through image capture, so we don't have to rely on manual interpretation. So let's break it down. The workflow is fairly simple. Phages will first be mixed with a redox-sensitive dye that is known as resozurin in this well insert. This is able to detect actively growing cells. Resozurin starts off as blue, but when bacteria are metabolically active, the dye gets reduced and it turns into its pink form known as resorufin. The chemical reaction is shown over here. The bacteria are going to be loaded into a separate reservoir. We can see the 4 wells here. And this post slider gets slid over the reservoir so all of the notches interact with the bacteria. And then this gets pushed down into the phage well insert so the bacteria can actually make contact with the phage dye mixture. The idea is that upon interaction, if the phage is effective in lysing the bacteria, the dye should remain this bluish or purple color. But if the bacteria aren't susceptible to that phage and they continue growing, the dye will shift to pink. We have tested the RD or rapid detection device against 2 conventional methods, the 96-well plate and the spot test. Testing was performed in 2 E. coli strains, UTI 89, which is our mouse model cystitis strain, kind of like our lab UTI strain, which is shown over here. And then we also have UHT1, which is a clinical UTI isolate. We screened 10 phages in replicate, and we can see the phage maps over here. All of these phages are derived from the Felix Durrell collection over at Université Laval, along with 2 negative controls, either with or without an unsuccessful phage, SB1, which is an Acinetobacter phage, so it does not infect E. coli. The rapid detection device is able to distinguish effective from ineffective phages based off of their bacterial growth trends, and there is agreement between traditional methods. Importantly, the RD makes interpretation consistent between the solid and the liquid-based assays, which addresses the common discrepancy between the 2. This assay is completed in approximately 2 hours, which is a clinically relevant time frame. And even though the 96-well plate assay can also be performed within that time, it's more labor and resource intensive. We are still working on testing the device out with a larger E. coli isolate collection and phages, but we also want to work with other organisms that are prevalent in UTIs, such as Pseudomonas aeruginosa. We would also like to include an element of urine stability testing with this device to see one side if phages can actually retain stability and infectivity in urine, and also if the bacteria can still be lysed and the device is able to detect this lysis. This allows us to better mimic clinical environments. There's also an aspect of looking into the biofilm degradation capacity of various phages as well, because biofilms are very common in complicated UTIs. So on one side of things, the rapid detection device is like this phage on a cassette platform. If you thought that was cool, it actually gets even better. Our collaborators over at Dr. Aaron Wheeler's lab, including his PhD student Bernadette, they have been working on developing a microfluidics-based platform for this testing, which is like an even cooler phage on a chip approach. This is a video on how the device works. So on one side of the chip, you have your bacteria. On the other side, you have your phages mixed with your DNA dye. And with these electrostatic forces, both can interact with each other. Here are the results we get preliminarily. We are measuring fluorescence over here. ECB is our positive control of just E. coli cells, and at different multiplicities of infections or phage bacterium ratios, we can see how fluorescence intensity is diminishing as phage numbers increase because there are less bacterial cells that are actively growing and fluorescing. So to end off, if you remember one thing from my talk, it's this. Fertility testing needs to be improved. It needs to be faster and more user-friendly, but more importantly, it needs to be standardized so that if you and I were to test the same bacterial isolate against a set of phages, we can get the same results. And our take on this is using a rapid detection device along with microfluidic devices that make this possible. Finally, I would like to say thank you for your time, and especially thank you for giving an opportunity to all of those who have supported this work, and I'm happy to take any questions.